Welcome to our video on activation functions in neural networks. Activation functions are a crucial component of artificial neural networks. They introduce non-linearity, allowing neural networks to learn complex patterns and solve sophisticated problems. Today, we'll focus on two of the most popular activation functions, the rectified linear unit, or ReLU, and the sigmoid function. Before we dive into specific activation functions, let's understand why they are necessary. Without activation functions, a neural network would be nothing more than a linear regression model, regardless of how many layers it has. This is because composing multiple linear functions still results in a linear function. Linear models are limited in their ability to represent complex relationships in data. They can only learn straight-line boundaries, which are inadequate for most real-world problems. Activation functions introduce nonlinearity into the network, allowing it to learn more complex patterns and relationships. This is what gives neural networks their power and flexibility. Let's examine how a neuron works in a neural network. Each neuron receives weighted inputs from the previous layer. These inputs are summed together, along with a biased term, to produce what we call the preactivation, or Z. The activation function then transforms this preactivation value to produce the neuron's output. Mathematically, we can express this as the output equals the activation function, F applied to the preactivation Z, where Z equals the weight matrix W times the input, X plus the bias B. Now, let's look at our first activation function, the rectified linear unit, or ReLU. The ReLU function is defined as Fz equals max 0 Z. In simple terms, ReLU outputs 0 for any negative input, and for positive inputs, it outputs the input value itself. Here's what the ReLU function looks like graphically. As you can see, it's flat at 0 for all negative inputs, and then increases linearly for positive inputs. The derivative of ReLU is also simple. It's 0 for negative inputs and 1 for positive inputs. This simplicity makes ReLU computationally efficient. Key advantages of ReLU include: it introduces nonlinearity without affecting positive activations. It's computationally efficient. It helps mitigate the vanishing gradient problem, which we'll discuss later. One notable issue with ReLU is the dying ReLU problem. If a neuron's weights are updated in such a way that it produces only negative outputs, its gradient will be 0, and the neuron might never activate again. This is called neuron death. To address this, variants like leaky ReLU have been developed, which allow a small gradient for negative inputs. Now, let's look at our second activation function, the sigmoid function. The sigmoid function is defined as Fz equals 1 divided by 1 plus e to the power of negative z. This function squashes any input value to a range between 0 and 1. Here's the sigmoid function graphically. Notice how it creates an S-shaped curve that asymptotically approaches 0 for very negative values and 1 for very positive values. The derivative of the sigmoid function is f prime of z equals f of z times 1 minus f of z. It peaks at 0.25 when the input is 0 and approaches 0 as the magnitude of the input increases. Key properties of the sigmoid function include: it outputs values between 0 and 1, which can be interpreted as probabilities. It's smooth and differentiable everywhere. It has historically been popular for binary classification problems, however. The sigmoid function has some limitations. It suffers from the vanishing gradient problem for very positive or negative inputs. Its outputs are not zero-centered, which can make training more difficult. One important issue with activation functions is the vanishing gradient problem. When we train neural networks, we use a technique called backpropagation, which relies on computing gradients. If these gradients become very small, the network learns very slowly or not at all. Let's look at the sigmoid function's derivative again. Notice how it approaches 0 for large positive or negative inputs. If many neurons in a deep network are in these regions, gradients can become extremely small as they're multiplied during backpropagation. This is where ReLU has an advantage. Its derivative is either 0 or 1, so for positive inputs, the gradient doesn't diminish. This allows for faster and more effective training, especially in deep networks. Let's summarize and compare ReLU and sigmoid activation functions. ReLU, defined as max 0 Z, fast to compute and differentiate, helps avoid vanishing gradient for positive inputs, can suffer from dying ReLU problem, commonly used in hidden layers sigmoid, defined as 1 over 1 plus e to the power of negative z. Outputs between 0 and 1 probability interpretation, suffers from vanishing gradient. Historically used in the output layer for binary classification in modern deep neural networks, ReLU is typically used for hidden layers due to its computational efficiency and effectiveness in avoiding vanishing gradients. Sigmoid is often used in the output layer of binary classification problems for its probability interpretation. There are many other activation functions as well, such as tan, leaky ReLU, YeLU, and JeLU, each with their own advantages and use cases. In conclusion, activation functions are a crucial component of neural networks that enable them to learn complex, nonlinear relationships in data. ReLU has become the standard choice for hidden layers due to its computational efficiency and effectiveness in mitigating the vanishing gradient problem. Sigmoid remains useful for binary classification output layers. As the field of deep learning evolves, new activation functions continue to be developed, each with their own strengths and applications. Understanding when and how to use different activation functions is essential for designing effective neural networks. Thank you for watching.